Bryan, how you doing, man?
Good. Doing good up here. I'm just getting over being sick. But I'm glad that I'm going to be healthy to travel.
There you
January is a
go.
big travel month.
Where are you going?
Well, SHOT Show, of course, but before that, there's a conference that I go to the week before SHOT Show.
Hmm.
So it's nearly 2 straight weeks of travel coming up that I leave for on Sunday.
I see. Yeah, I'm gonna be at shot as well. It's gonna be a good time.
hmm
Well,
Yeah, if you come home from SHOT and you're not sick carrying some kind of germ, your immune system wins an award.
well, I am in Texas, and we eat a lot of Mexican food, deep fried, and we eat bacon wrapped bacon. So, you know,
That'll do it. That
so hopefully it's enough that it'll keep me healthy enough because I got to go to Southwest Nationals right after. Like
Mm,
weeks after. So I'm
yeah.
hoping I'm ready to go for that. But anyway, let's jump in, man. Let's not beat around the bush. Everybody's been asking about this, so let's just jump right into it.
Okay.
Barrel cleaning. Where are you at on
hmm
that?
Um, well, the way I view barrel cleaning is there's two basic different approaches to it. You can use solvents to dissolve things out of a barrel, or you can use abrasives to abrade things out of the barrel. And I've done both over the years. And one of the challenges with cleaning for someone like me who likes to quantify and put numbers on things is like, how do you know when you've done it right? How do you know there's no very clear and obvious feedback when you've cleaned a barrel correctly? Now, you can obviously look in with a bore scope and see if there's anything in there or not. And that's one measure of how effective your cleaning is. But how does that affect your shooting? And that's the part that I've had trouble correlating the effectiveness of cleaning with is like, what effect does it have on your shooting? And so, long story short, we have converged. I've converged on an abrasive type of cleaning, usually with JB bore paste, sometimes with witch's brew. It quickly removes a lot of the fouling. But what I find the benefit of abrasives is in addition to removing the fouling, it's also smoothing the barrel steel as well, right? So that if you've got like little fire cracking or sharp edges in there that are picking up copper fouling, the chemical solvents can dissolve them away, but those features are still there that are going to grab the fouling right away again. But with abrasives, it works a little bit to smooth the barrel out so that it doesn't pick up the fouling as much. And so that's why for the last near the end of my F class shooting days is when I converged on that. And we use it a lot for the large caliber testing that we've done a lot of work with lately, 375s and 338s. Um, so that's a long answer. There's a whole lot more I could talk about on it, but not to get too far down the road.
What about the cleaning intervals? How long do you go before you clean?
Um, it depends on the cartridge. Something like a 22 rimfire, I don't know how often or if ever, what I would say for cleaning those. They don't seem to respond other than when you clean them, it takes some shots to get the barrel shot back in again. With something like, a high performance ELR cartridge, every 100 to 200 rounds is what I would consider a good interval to clean. And, with 308s, with F class kind of stuff, a lot of times I'd shoot a whole tournament without cleaning and just clean in between. I'll put it this way. As I progressed through the years and tried to use my experience to learn from with cleaning, my cleaning intervals got larger, not shorter. Okay. So I typically, because once you clean, then it takes an amount of shots to get things back to normal. And I can't say that I've really commonly seen my precision or anything measurable about shooting fall off after 100 or 200 rounds. Things seem to shoot really well for a long time, especially in new barrels. Now, as a barrel gets older, you get 1,500, 2,000 rounds on a 308 barrel. And I think a shorter cleaning interval at the end of the barrel life, it makes sense,
What
as
you
opposed
say?
to when it's new.
You said it shoots really good. What's your I guess what are you looking for? What were you looking for when we're shooting FTR? Because you were shooting FTR 308. So what was your baseline?
Well, the base, I've always thought of that gun as shooting about a 0.6 average. 0.6 minute, 5-shot groups at 100 yards is what the baseline precision standard is for me in that gun. I say standard, that's just the long-term running average over time. And, that translates to something bigger at long range, obviously. And how much bigger is a confluence of all the variables, muzzle velocity spread, mirage, how much grass is under the bipod mat, all those kind of things matter. And so when I say I didn't see my groups open up as a result of the barrel being fouled, it's not to say they never opened up. A lot of times, when I've had a lot of rounds on the barrel, my groups got bigger, but I always attributed that to some other condition like heavy mirage or a non-optimal shooting position or something else explained the groups being bigger other than, there's, oh no, I crossed 200 rounds. Now it's fouled out. So I guess suffering from my barrel not being clean isn't something that I've really suffered from.
Do you think if your goal was, I don't know, let's say quarter minute, you would possibly shorten your cleaning spacing?
I don't know.
The reason I ask is because anyway, go ahead.
Yeah, that's less than half the group size that I'm accustomed to shooting in FTR. So I'm sure that at that level, there are other variables that will, the signal will rise above the noise when you're averaging quarter minute groups as when you're averaging 0.6. And so maybe if you're shooting a gun that precise, the consequences of fouling will become obvious sooner than if you're averaging 0.6. So yeah, I really can't say what would happen if I did that.
Well, the reason I ask is, bench risk shooters, right? They clean every 15 shots, and they'll say things like, well, my gun was shooting 180s when it should have been shooting 130s. So I cleaned it some more and it shrunk the groups back down. They live in a whole different world, the kind of world that I want to live in one day. But I do take their experience and try to apply it as much as I can to because it doesn't hurt to over clean. Do you think it hurts anything?
Not if you're cleaning correctly. I mean, if you have bad cleaning habits that you're doing damage, then you probably could hurt. But that's not from over cleaning. That's from improper cleaning.
Correct. I'm just saying instead of going, I guess I kind of compare it to oil changes, right? We all change oil at 3,000 miles or whatever, 5,000, right? You could probably go 8,000 or 10,000, but it doesn't hurt to go 3,000. You know what I'm saying? And that's kind of what I'm wondering. That's kind of because the barrel is not the same barrel from 100 to 200 as it is from 1,500 to 1,700. I just never know where that fall off is going to be. At some point, I'm going to fall off that window. You know what I mean? And I think, at least for myself, we go, in F class 75 to 100 rounds, and I just clean it just because it's convenient, right? We're done shooting for the day. It's a pretty easy thing to do just to clean it. But, I just always wondered what your experience was, shooting TR. And I think, obviously, expectations change your approach as they should.
Yeah. The expectations. So in the last few years, we haven't talked in a long time.
Yeah.
And we've been busy the last few years with some government contracts, and that engaging those activities has taught me some things that, all those years of competition shooting, I never would have had the opportunity to see. And one of the things that we do in those tests is barrel life cycle tests. So take a brand new barrel and fire the same ammunition in it from the first shot to 1,000 rounds or 1,500, whatever the test is designed for. And never change the load, not once. And what you're doing is studying the effects of the barrel wear over time. Because, obviously, if you're changing the load to always keep it optimal with the barrel, you can't do that and also see how the barrel's changing itself at the same time.
Right.
And so with these life cycle tests, we'll take a barrel and, 1,000 rounds, and we'll just start shooting 5-shot groups or 10-shot groups, depending on what it is. And everything's instrumented, every shot is chronographed, or usually with the radar. So we're getting BC, muzzle velocity, group size for an entire life of the barrel. And that really opened my eyes to a number of things. One of the things that opened my eyes up to was the migration of muzzle velocity that happens naturally through the life of a barrel. That's not a result of temperature on your powder or a different load. It's literally the same ammo and you're just shooting it continuously. We'll burn a barrel out in a week or two with 1,000 or 1,500 rounds on it. And so not much is changing in that time, but yet we'll see the muzzle velocity start at, say, 2750. And within 100 rounds, it's 2850. And we clean it. And when you clean with abrasives, it'll set back the velocity a little bit too. And then it'll start climbing again. And so you see all these trends that are a feature of the barrel life cycle playing out, not a result of like a different load or a different temperature, but it's literally just the barrel going through its life. So seeing the amount of velocity migration that is typical in a barrel, as well as how that velocity migration responds to cleaning and different types of cleaning, those were really eye-opening. So when you clean with solvents, when you remove all the copper and carbon fouling from a barrel using solvents, but you leave the barrel steel the same, you're likely to pick up at very close to the same velocity that you left off at prior to cleaning. But when you clean with abrasives, that often will set back. Well, it will set back a much greater amount what your muzzle velocity is. So if you picked up 100 feet a second and now you're seeing pressure, clean with abrasives, and that's going to set the velocity back and, push your pressure problem down the road a little further, I guess. So those are some of the eye-opening things. Also, the statistics of large sample sizes with groups is something that I came into awareness of with shooting these life cycle tests. So again, how many other applications would you shoot an entire barrel life with the same exact ammo? That's just not something that a lot of precision shooters do. Even if you shoot factory ammo, you go through different lots of it. With hand loading, you change components at some point. But when you have 1,000 rounds of the same ammo made from the same components and you're shooting groups, I'm talking hundreds of 5-shot groups. And, some of those groups are big and some of them are small. And I'm talking back to back. You can shoot a half-minute group and a minute-and-a-half group back to back with nothing different. And that is not only possible, but it's statistically unavoidable that you're going to have outliers. And prior to doing this testing, I treated outliers like every other hand loader, like we all did, which was, if you have a flyer, there's a reason for that flyer and you can discount it and you don't have to average it in with your group. You can talk yourself into thinking that you pulled the shot or whatever. But by shooting this many groups, I've seen enough outliers, both large and small. And whenever I look close and really analyze what's going on, it is nothing different than a normal distribution. It's a bell curve distribution of group sizes that a gun will shoot. And it's not like it's good when it's new and bad when it's old, or good in the middle, or it's basically just, static all the way through. There's an amount of noise that's your baseline. And what we found is that noise level on group size is about a 30% standard deviation. I'll explain what that means. So if you have a gun that's, to make the numbers easy, we'll say if you have a gun averaging 1 minute of angle groups, a 30% standard deviation is 0.3 minute plus or minus. And statistically, you're going to have 67% of your samples within plus or minus 1 standard deviation. All right, so if you're averaging 1 minute, you're going to have 67% of your groups between 0.7 and 1.3. okay, plus or minus 0.3, that's 30%. So 67% of your groups will be from 0.7 to 1.3 naturally. There's nothing good about the 0.7s or bad about the 1.3s. They're all part of the same population. All right. And likewise, if you go plus or minus 2 standard deviations, that's 95%. That's 19 out of 20 groups are going to be between, let's see, 0.4 and 1.6. So now you're plus or minus 0.6 on your 1 minute. And that is completely natural. That is a completely natural distribution of group sizes. So if you sit down with your rifle and start with a full box of ammo and 100 rounds, and you shoot 5-shot groups, you're going to shoot 20 of them. And from this distribution that we've observed in large sample testing, if the overall average of that 100 shots is 1-inch 5-shot groups, I'm saying there's going to be a group in there that's a 0.4, and there's going to be a group in there that's a 1.6. That's 19 out of 20, and you've shot 20 groups. And I think that really internalizing that reality of distribution and group sizes changes the way that we look at a lot of the load development techniques that we do, right? Because we do load development on, say, seating depth or powder charge, and we're looking for differences in group size. Like, hey, if I can make my 0.6 average into a 0.5, then I'll take that every day of the week. But what we're missing there is that truly our ability to resolve a 0.1 difference in group size is not what we think it is, because we're dealing with 3 times that amount in natural group variation anyway. So those are some of the insights that I've got from the large sample testing with this contract work that requires it, is, the life cycle effects over the life of a barrel, and also the natural statistical distribution of group sizes, and how that affects the cause and effect thinking in other areas of hand loading and shooting.
The Hornady guys on their podcast, they've been talking about that. They had a couple of podcasts back to back, and actually Jayden Quinlan's going to be here next week on my podcast. We're going to discuss precisely what you just talked about. However, I'm going to push back a little bit, and because at what point do things change? Because benchless guys, if they don't have a gun, if they have a rifle that shoots more than 1/4 inch at 100 yards, like, that's no good to them, right? And they have tons of them. I'm sure you've seen Mr. Walt Berger, whom you knew very well. I mean, he was a big benchless guy, and these guys are shooting tiny dots all day long, literally, right? And their averages are, Bart Souter, who was on my podcast, he shot 5 days, 3 different rifles, 150 shots total, and his average was 0.250. Mm-hmm. Right? And I just wonder how that happens. Is it I don't know. I mean, I honestly don't know.
So yeah, that's just it's just shifting the average from, I gave an example as an average of 1 minute of angle just to make the math easy.
Right.
But you can do the same thing. If the average is a 1/4 minute, okay, let me see, 1/4 minute times 30%, that's 0.075. All right, times 2 for the 95%, that's 0.038. Okay. So if you were to look at Bart's groups, like his aggregate at the end was 0.25 out of all the 5-shot groups. But if you looked at each individual 5-shot group, I'm betting they ranged from 0.25 minus 38 thou to 0.25 plus 38 thou. So I could do that. I don't want to get wrapped around the axle with numbers, but the same point is that your average is made up of samples that are smaller than average and also larger than average. And whether the average is 1/4 minute or 1 minute, that same thing applies. That 30% that I'm citing, where that comes from is actually, like, we shot hundreds of groups and we just simply take the standard deviation of all of them. And it holds for Francis's PRS gun, which averages 0.4 minutes at 100. and it holds for my F-class gun that averages 0.6, and it also holds for the big 375 guns that we're working with that average closer to 1 minute. That's why we say that it's a percentage standard deviation, not a fixed number.
Now, what about? But see, you guys are using the exact same load the whole time, right? Mm-hmm. These benchers guys, they change their loads all day long. Do you think it's that noise is in the actual data, in a sense of what do you call it? Like enough shots is just gonna make things worse and better, or is it simply that the load is not keeping up with whatever the benchers guys keep up with to keep those groups that small? Because if you ever heard or talked to benchers guys, they're changing their load all day long to keep shooting small groups, and that's one thing I don't have an answer for.
And I don't either. I mean, I haven't been close enough to bench rest shooting to really, internalize and understand what they do and why they do it. I mean, obviously, I've had a lot of conversations. I've been to the matches. I've seen it. One thing that's different about their shooting application than any other that I know of is they carry powder to the range and load from a powder meter right there in between stages. So that having the powder exposed to the environment, we know about the effects of humidity on powder when it's exposed to different ambient conditions. So that's one variable involved in bench rest shooting that is not present in most other, where you take your ammo that's already assembled.
Well, that's precisely why they do it, so they can change the load as the day goes on, because they, depending, these guys read they read the groups like reading a book, and they go, oh, this group is looking this way or that way or whatever, right? And then they make adjustments based on that. I had Jack Neary on the podcast, and he explained what the groups look like and what you do to fix it. And I mean, and these guys are like, you and I will both lose the farm if we shot against them. You know what I'm saying? And I'm going, what do they know that we don't know? Because and this all falls back into the big noise. To me, everything's noisy, right? Like we can just talk about small sampling. Well, maybe the test that you did itself is a small sample of the big picture, right? And that's what allowed you to arrive to that conclusion. But if you were to test the exact same test with a different load, or I don't know. Again, I don't even know what I'm saying. All I know is I wish I knew what these guys know, because that would be amazingly helpful for me in F-class, right? If I could always have the gun in tune, or as close to in tune as possible.
Yeah.
Anyway, so, I don't know.
Yeah. So more on bench rest, like I guarantee 100% that the bench rest guys know more and are better at shooting small aggregates in bench rest than I am. Okay. It's not that I don't know anything about bench rest that they don't know. I think that the awareness of normal statistical variation in group sizes is something that is not considered in bench rest to explain why groups are bigger or smaller. Like you said, they can look at a target and read the groups and tell you all kinds of things about the gun's tune and whatnot. But I wonder how does that account for the fact that there is natural statistical variation? You know what I mean? Like,
and that's what I don't know.
It was just random.
And that's the question that I have, right? It's like, if I guess what you're saying, if I'm hearing you correctly, is that if they just shot the exact same load all day long, it probably the results would not be hardly any different.
I'm saying when we shoot the same load all day long, we have as much variation in our group sizes as there is in every other shooting discipline that we see.
Right. Well, that's what I'm asking is, do you think if they never changed the load, the results would be similar?
I don't know. I mean, like I said, there's a lot that I don't know about bench rest. And if they shot the same load all day long, now, if they loaded in between yard lines like they do, the same load all day long, then they might not stay optimized, or the true baseline of precision may change. However, if they loaded all ammo before going to the match and kept it controlled, then maybe doing it that way prevents them from at least exposing the powder to the environment.
Well, that's what we do in F class. That's what we do, right? We preload.
Yeah. So, and we still have a variation in group size in F class, but there's different nuances with each discipline. And when I look at bench rest and see all that exposed powder out on the firing line, it's like that's an exposure to a variable that doesn't exist, at least not to that extent in other shooting disciplines. So I have to wonder if the chasing of the tune throughout the day isn't at least partially necessary, because the powder itself is changing and picking up or losing moisture throughout the day. Like any typical day starts out, dewy, moist, depending on where you're at. But it's common to have dew and high humidity, colder temperatures in the morning. And then as the day heats up, temperature goes up, humidity goes down. And if your powder is exposed to that, it's potentially gaining and losing moisture as well. So when you say you're changing, or the bench resters are changing their load to keep up with conditions, are they really just changing the powder charge to equal the same thing if the powder were all the same humidity?
I see.
And so, yeah, I don't know.
Yeah. So in F class, as you know, we preload because we don't have time to load in between. And, we figure out ways to kind of stay in tune, and that's barrel tuners. But anyway, we can talk about that later, because that's going to be a huge topic. Let's cover some of these others. That I made some notes, and
okay.
But anyway, so we'd covered barrel cleaning. You touched on powder humidity, which I wanted to talk about. So how big are the effects of powder humidity?
Oh man, it can be huge. I'll give you the answer to your question to scope how big of a difference it can be. In a 6.5 Creedmoor with 140s, okay, we took a very common setup. 6.5 Creedmoor, 140 hybrids, and Hodgson's 4350. And I don't at this time remember exactly what the load was, but we picked a nominal safe load, and we dispensed all the powder charges into the cases. And then we took some of those cases before seeding bullets and put them in an ammo can with desiccant to pull the humidity down as low as we could. And we put a Kestrel drop in there to monitor the ambient humidity in the can and let it soak for a couple days. A different sample of the ammo, like same ammo, we took a sample and put in a different ammo can with humidity packs that pulled the humidity to like 84% or 88%. And so we're pulling the humidity of that powder apart. And then we seeded bullets on it periodically over time. Like after 2 days, we did a test, 2 more days, tested again to see like how long it took for the powder to acclimate. And at the end of 2 days of the powder soaking either with desiccant to be dry or to be at 88%, the difference in muzzle velocity was 200 feet per second. 200 feet per second with a 6.5 Creedmoor and 140s with the same charge of the same lot of powder. Everything the same
weight,
other than the humidity. Same weight, yeah. Everything the same except for the humidity environment that the powder was stored in.
Do you think the volume would be the same? Because remember, maybe that's why I just thought about that. Maybe that's what bench rest guys throw with a powder throw, which is by volume, not by weight. Anyway, I don't know. That just crossed my mind.
I don't know either.
But so if you had because the volume would be the same, right? For example, if you have a humid powder and then you dry it out, the volume never changed, correct?
I wouldn't think could change much.
Yeah, I mean, I don't think the kernels would shrink or expand.
One thing we have on that, so
we
had a load of like 130 grains of powder, and I put it on a scale, and over time, watched the weight of that charge change. So like it came out of a jug that was at 60%, and I think the environment was 30%. And after 24 hours, it lost like a grain of weight. All right. And I'm checking the scale with the check weight too, to make sure that it's not drifting. So that's accounted for. And it lost about 1 grain out of 130 due to moisture. And how much that would affect the size of the kernels and the volume, I don't know. We didn't measure that.
Yeah, that's what I'm saying. I mean, I can see how it would affect weight. I mean, I was in construction for a very long time, and everybody knew that if you're going to order sand, order it before the rain because you get more sand.
Oh yeah.
You know what I mean? But it's maybe something else to consider. Like perhaps, number one, we obviously need to be keeping track of humidity. And number two, maybe we need to be loading by volume rather than by weight.
I wouldn't go there. We've tested volumetric and weighed a lot of times, and weighing powder is a more reliable way to get a consistent amount of energy in the powder charge than by volume.
Okay.
It's the mass of the energetic material.
Right. Okay. Fair enough.
And also on powder humidity, like that's how much of a difference it can make. But I think it's really interesting, the problem that can solve, right? Like the way we came about it or even studied in the first place was because we used to have a problem when we travel with ammo, right? We load in Michigan and drive all of our stuff to Phoenix or to Raton or someplace like that. And, some of us, we'd get there and our SDs and average muzzle velocities would be the same. Other times we'd get there and our SDs would be doubled. And we didn't know why. It didn't even have to be cross country. One time we were doing a BC test with 375s. We had ammo loaded in Michigan at our lab. And on an evening, it was very humid. And then we packed it up and drove it. And within a day or two, we were shooting it in Ohio on a warm, sunny, dry day. And from the velocity and pressure that we saw in load development, which was all good, 2 days later, we shot the same ammo out of the same gun. And it was so hot, it was 200 feet a second faster and blowing primers. And we're thinking, how in the world did this ammo that behaved like this 2 days ago now suddenly behave like this when everything's the same? And in retrospect, now I remember the moisture scenario, but that's the problem that we were having from the humidity in the powder. Is when you travel, if you load the powder and your powder's conditioned to say 80% humidity, and you pack it up and you travel to a place where the ambient humidity is 30%, if your rounds are all sealed hermetically from the environment, you won't have a problem, okay? Also, if your rounds are very leaky and not sealed, and they're in the new environment long enough that they can all equalize, your velocity average may change, but your standard deviation likely will not, because they're all consistent if they all equalize. Where you have a problem is if your rounds some of them are sealed better than others, and you have to shoot the match at a point where the leakier cartridges have acclimated more to the ambient condition than the less leaky cartridges. That's why your SDs are big. And whenever we started doing these studies with humidity and observing these effects, we started putting the humidity control packs in our ammo boxes when we traveled, and we don't have that problem anymore. So that's the big takeaway I want your listeners to have from this is of all the stuff we do, look, a lot of the stuff we do, I struggle to find the practical application. It's just neat to know, or it's fun to know, or it's only applicable to a very small group. But this is a problem that has plagued every competitive shooter that has traveled with ammo intermittently for a lifetime. And so I think I wanted that to come through, because that was the big takeaway from our powder humidity study was keep, your powder jugs that you load from, be mindful of conditioning those, and also your ammo, condition it all the way through to the competition, and your SDs will be the same in the match as they were when you were doing load development.
So you're saying is keep your powder dry.
Keep your powder the same amount of wet.
Okay. Um, we
too dry can be a problem. Actually, that's where you'd see pressure spike. Like
well,
if you had 80% and you acclimated to zero, I mean, what would 200 feet a second more look like in pressure?
if
So
it was
keep your
always
powder
this,
dry.
I think the problem is with the variance. If it was always the same, it shouldn't matter whether it's wet or dry, right? As long as it's consistent.
Yeah, the same from when you
Yeah.
develop the load to when you shoot the match. You want
Yeah.
that humidity.
I don't have, humidity packs or anything in my powder, but I keep my reloading room at 75 degrees year round, and my AC has humidity setting, and it's set at 50%. And so, obviously it varies, but not by much. So that's kind of how I deal with it. You touched on barrels and cleaning and all that, but what about barrel break-in? That's a topic that it's just one of those that I've used to break in barrels religiously because that's what the manufacturers told me to do, and the more I shot, the less I don't break in barrels anymore. So what's the data on that you guys have found?
Yeah, very similar to your experience. Like many years ago when getting a new custom barrel for competition was something that I saved my McDonald's money for. I worked at McDonald's when I was a teenager. Like when you get your first new custom barrel, you want to do everything you can to take care of it, make sure it's going to give you a good long life. And, I did all that break-in stuff then because you don't know and you only get one shot at it. But over the years, like we've gone through hundreds and hundreds of barrels now, and with various different efforts of break-in. And I think there might be a benefit. See, here's the thing. If your barrel has a particular problem that breaking it in would solve, then of course, break it in that way and alleviate that problem. But I think that most of the top end custom barrels that any competitor is going to have available to them to put on a, competition rifle, they don't have those problems usually. I think maybe factory barrels that are rougher, have tool marks, they might foul more aggressively if you don't break them in because they're not hand lapped, they're not custom barrels. So I think it's a very condition specific thing to do. We fall into a thinking trap of does it work, does it not? That black and white thinking. But I think it's way better to ask the question, under what circumstances would this matter? And are those circumstances present in my system? I think that's a much more intelligent way to approach these lines of inquiry about, barrel break-in, effects of think of any gadget or device in shooting and think of what problem it solves and ask yourself if you have that problem or if you have the conditions under which that device is going to help. And I look at barrel break-in the same way. If you got a rough factory barrel, hey man, I'd probably break that in at least with some fire lapping rounds to like get aggressive at removing those tool marks and then, give it some finer polishing with abrasive. But if you look down a new barrel that a competition gunsmith put on your rifle and that sucker's like a mirror, what are you breaking in? What exactly are you doing with the break-in process? I don't think it's necessary or really even does anything if you start with a barrel that's already that good.
Well, my take has always been if it's dirty, clean it. And if you have a barrel that fouls real bad real fast, then yeah, clean it. And I guess that would fall under break-in. But again, I don't know anything about intervals. I don't believe in the whole one-shot thing, right? If anything, if you think that's going to do anything, I would just go in there from the get-go and give it a good scrubbing with some abrasives and smooth some of that stuff out and then just start shooting and clean it 20, 30, whatever. But again, whatever falls back to whatever makes you feel good about it, that's the right answer. Because you can't if you don't have a barrel that's shot and you call the manufacturer and say, hey, this barrel just doesn't shoot, and you send it back and they have absolutely no way to prove whether you whether you broke it in or not, which tells me if they can't tell, it probably doesn't matter.
Yeah, that's a good reasoning that I use a lot. If you can't tell, if you can't be measured, if it can't be detected in any way, it probably doesn't matter. That's
yep.
It makes sense.
Now, what makes barrels speed up?
I've got a theory about that. It's a working mental model, but I don't have enough experience or direct instrumented testing with internal ballistics to say this is fact, but I can give you my version of why I think barrels speed up. Okay. So, and I arrive at this through correlations. Like, what are the correlates to barrels speeding up? Well, from what we've seen, like the first 100 rounds tends to be the most aggressive, and from 100 to 200, it's less aggressive. And then after 200 rounds, you're speeding up very, very little. Now, in watching a barrel in those first 200 rounds and seeing how it's changing, one thing you notice is the formation of fire cracking, right? It starts out very, very small. And so for the first 20, 30 rounds where there's no fire cracking, doesn't start to pick up speed yet. But when you get an amount of fire cracking, an amount of fouling in the barrel, that's when you start seeing the velocity start migrating up. And like I mentioned earlier, if you clean the barrel with abrasives, it will set back that velocity migration. So we know that we can watch fire cracking form in correlation to velocity going up. And we notice that when we do something that smooths the barrel, velocity is set back. So from that, I deduce that the roughness of the inside of the barrel correlates to muzzle velocity. And I think the mechanism that happens is it builds back pressure on the powder burn. All right, imagine if a bullet just slipped down a barrel with no friction, no engraving force, no friction. It just popped right out the end of the barrel. That scenario would not develop the back pressure. Just the inertia of the bullet itself doesn't develop enough back pressure to fully burn the powder charge and get all of the pressure and energy out of it. But you start resisting that bullet's motion, it has to engrave the riflings, and that resists the motion, and the powder burn spikes and you get more velocity and pressure. Well, as you add friction to the barrel and you make it harder for the bullet to move out of the way, that causes a feedback loop with the powder burn. The powder burns faster, hotter. You get more velocity out of the same powder charge because the barrel is giving you more back pressure through friction. Does that make sense? That's kind of my model of it. Because everything we do to affect barrel friction affects his velocity.
It makes sense, but why does it stabilize? Because it speeds up and then it stabilizes, but yet fire cracking doesn't stabilize. So why does speed stabilize? If they are a direct relationship, why would one stabilize and not the other?
That's a good question. I think that maybe going from the smooth, like the mirror finish new barrel, to any fire cracking at all is the biggest change in friction that you get. And although friction may continue to increase as fire cracking gets worse, it's not nearly as much as going from smooth to fire cracked. And that's why, like, after 200 rounds, velocity does continue to speed up, just not very much.
Well, okay. I got another question. As you were talking, something else popped into my head. A sign that a lot of shooters use that the barrel's gone is that it actually slows down.
Okay.
Have you heard that before? Is that a thing?
We've seen that, yeah, in barrels where they'll.
So again, that now. So now that contradicts this as well.
Well,
these are just things that are going through my head as we're talking.
Oh no, it's really good. I do the same thing. Like the moment I start to think I'm connecting dots, I try to start thinking of why that wouldn't be the case. Like what observations are for and against. And when a barrel slows down at the end of its life is a perfect point about, well, if it's getting worse and worse the whole time. So, and this is where measurement starts to become important. And we don't yet have the instrumentation to measure fine details of barrel dimensions on the inside and surface roughness and things like that. But what I would say, in the cases where we have done life cycle testing through the peak of velocity and seen it start to come down, those are barrels that by that point, there's a very high degree of erosion in the throat. Okay. The riflings that started out 4 thousandths tall on each side are now down to like 2 thousandths tall. And so, yes, the fire cracking is worse, but the riflings, the throat, all of that stuff itself has eroded to a larger diameter. So although friction may be greater on the surface, the overall dimensions of the hole that the bullet is going into is also larger. So that's a decrease in resistance. You know what I mean?
Yeah.
So I think a lot of the powder burn stuff is set up in that first couple inches of when the bullet's engraving and starts going down the barrel. I think it gets a lot less sensitive once that volume expands to be, 6 or 7 bullet lengths. But in that first engraving process, there's a lot of initial internal ballistic conditions that are set up. And so when that throat erodes and those riflings aren't engraving as deep initially, I think that sets up a much gentler and lower pressure spike, which is the initial condition for the whole powder burn and gives you lower velocity in that condition.
I see. Makes sense to some degree.
Like I said, I'm not putting my hand on the Bible saying this is exactly how it works, because I won't do that until we have the measurements and the instrumentation. But it's my best guess at what's going on based on observing life cycle tests of multiple barrels, with bore scopes and cleaning and documentation.
Right. Bullet sorting. Where are you at on that? Back in back when you used to shoot F-class, my channel was in its first stages of being born. And I used to look at you for knowledge, right? And again, I'm to this day, I'm still learning and trying to find out what's best and what really helps. What have you, back then you told me base to ogive was the way to go for sorting. If you could only sort one way. And I did, but then Bob Bach, he was saying base to tip. And for me, having 1,000-yard range, it was real simple to just test both. And obviously, the most variance was found in base to tip versus base to ogive. So I figured I was going to see a big difference. And just through all the testing that I did, I found that base to tip was the way to go. Just because the most variance is found there. Is that still your belief, the base to ogive is the only way to go, or you think base to tip has some merits?
I think base to tip is now the better way of doing it. Those years ago, I remember that interview that you're talking about, and that was before. I mean, at that point, yes, we had done a lot of testing, but we've done a lot more since then. And as a result of all the testing we've done since then, we have seen more cases where the majority of variance is in the tip of the bullet and the overall length of the bullet. And so the bullet sorting question is a great one to illustrate the value of how you form questions, right? So like if you say, what's the best way to sort bullets? The reality is it depends on what kind of bullets you have. If you have solid bullets, I would advise you to sort them differently or not at all. If you have brand X of open tip match bullets, then I would advise you to sort based on what the biggest variance is in that particular type of bullet construction. If you're using bullets with plastic tips, well, the measurements mean something different. So it's very important to understand how your equipment relates to your components, relate to the components of the person who did the testing. And so with the bullets that most of us shoot in like F-class, for example, lead core, copper jacketed open tip match bullets, the biggest physical inconsistency in those bullets is the MEPLA, the tip. That's kind of like the remainder of everything that didn't conform to the swaging process. It goes to that point. And the problem is, though, that it's difficult to accurately measure a MEPLA diameter. That's the thing that's aerodynamically either presenting a large or small front to supersonic airflow. So the sensitivity is in the MEPLA diameter, but because it's difficult to measure with calipers and whatnot, measuring the overall length of the bullet is indicating something about the MEPLA diameter. So bullets that are shorter are bullets that have larger MEPLAs. I'm talking within a lot of bullets. Okay, you take a box of bullets, get your 3 shortest bullets and your 3 longest bullets, and you set them on their base and look down at them from the top. Your 3 shortest bullets are going to have wider MEPLAs, and your 3 longest bullets are going to have smaller MEPLAs. And that's the thing that actually makes them fly with a different ballistic coefficient. And that's another thing. Like when you say sorting bullets, what's the best way to sort bullets? First, it depends on what bullets you have. Second, how are you, like, what's your measure of merit for a successful sort? Is it the groups? Is it that you shoot better groups at 100 yards with them? Or is it that you shoot less vertical at 1,000 with them? And I think most people who know why they're sorting bullets would say it's your vertical at 1,000 is the reason you'd sort them. In particular, because you're sorting to try to minimize the shot-to-shot variation in BC, right? You don't want a large tip bullet in the same string of fire as a small tip bullet. One will hit low and one will hit high. That's the mechanism we're dealing with. So if a guy knows enough about that he should be sorting his bullets, but not enough to know why, and he's shooting groups at 100 yards, you'll not understand or see the benefit of bullet sorting. So all of these questions usually require some unpacking to see like what the conditions are, what the expectations are for the question and answer.
So you talked about MEPLAT diameter. So this is where bullet pointing comes in. Mm-hmm. What are the do's and don'ts, I guess, about bullet pointing? Just because that's a big topic, I know. So real quick, what's the do's and don'ts?
So don't overpoint. I guess that's the only way you could, that's the baddest way you could mess it up. You could ruin bullets if you get too aggressive with the setting and point them until you're actually crushing them. And that's easier to do than you think, because if you just pick a random bullet out of the box and start setting your bullet pointer until it's perfect, well, how do you know you didn't grab the shortest bullet in the box? It takes a sampling. And what I'll usually do is with a new box of bullets that I'm going to set up my pointer, I'll get my calipers and measure 10 or 15 bullets, and I'll take the longest one. Okay, the longest one that I find in a sample of 10 and 15 in a box. And I'll use that to set the die. And I'll set the die so that it closes the point about 2/3 of the way. 2/3 meaning how big was the air gap to beginning. And after you pointed it, that's what I mean. You're closing that air gap about 2/3. You never want to close it totally, because the very next thing you're going to do is crush the bullet. So
how can you tell if you crush the bullet?
Well, if you crush it bad enough, you can see a visual swell in the nose of the bullet below the part that you pointed. But I think you can damage a bullet even before it's visible by basically delaminating the jacket off of, because you think you're pushing the bullet this way, there's a jacket wrapped around a core. And so naturally, if you push it, it's going to bulge the jacket. And whether you visually detect it or not, believe me, the airflow at Mach 2.5 knows if there's a change in shape, and it'll show up on target.
I guess what I'm asking is, people want to know what's the limit, right? That they want to stay away from, because, 2/3 of the way, close it up 2/3 of the way. That is very hard to measure. Is there a certain way that they can measure to say, look, just stay away from this?
I would say stay away from ever closing the point until the metal comes together. Okay. You should always be able to see, if you can see air through the hole of the front of the bullet, it means that it can't be crushed, because you haven't yet closed it enough to where the next thing is you're going to buckle the jacket.
Okay.
So as long as you're touching it and not closing it all the way, I don't think you're damaging it.
Okay. Perfect. So you guys have, what do you call your custom drag models? What do you call that?
Custom drag models.
Is that what it's called?
Yeah.
Obviously for F-class, we really don't care, right? Hit the target.
There's sighters. Yeah.
But
what you're really looking for is the differences in atmospherics that will move your zero between times of shooting. But But I've done some PRS, and it was very frustrating for me to never be able to really match up my curve, right? And coming from F-class, this was a whole new thing that I never had to worry about. And it seemed like I was always bumping up my BC, bumping down my BC, speed, whatever. And I just never knew what to do. So that sent me into, like it's normal for me to do. I'm going to go do some research and try to figure out why, and I know you have your custom drag models. And I had Kalen Wojcik on the podcast, and I asked him the very same question. And he said, well, there's different things, which is radar derived versus BC derived drag models. What's the difference? Because I don't know. Can you explain the difference? Say that again. Radar derived.
Right, versus BC. Apparently one is simply just BC. Is that what you use? I don't know the difference. This is what I know that he told me. He says, well, there's radar derived and there's BC derived drag models.
Okay. I'm not sure I understand that framing of it, because it's mixing two things. So BCs versus CDMs, those are different ways of representing a drag model. Mm-hmm. Okay. But radar, you can use a radar to create a custom drag model or a BC. A radar is just an instrument, just like acoustic instruments can measure. So
I guess Hornady and Hornady was talking about doing something different that does not require BC. And this is why I'm confused, because everything I've always known is BC, right?
Yeah. Okay. So I'll start a little further back. So a ballistic coefficient is a characterization of your bullet's performance in relation to a standard. Okay. Such as G1 is a standard, G7 is a standard. There's other ones too. And basically, if you have and when I say a drag curve, what I'm referring to is the drag coefficient of the bullet at every Mach number that it flies through, right? So you have a different drag coefficient at Mach 2 than you do at Mach 1. And the characterization of that can be approximated with standard curves. And when you do that, that's when you're using BCs. Okay, it's like a performance index. Here's how you compare to a benchmark that is G1 or G7. And the reason that BCs came into use was because go back to World War I, World War II, guess what everyone on the battlefield didn't have was a smartphone with a ballistic solver, right? So we needed fire solutions that could be calculated, and BCs are basically a computational shortcut because it allows you to get your ballistics from tables, prepared tables, rather than compute them on the fly. And so that's why BCs came into use in the first place, and they're still very useful. What they suffer from is that because you are comparing the drag of your bullet to a standard, you can make that 100% accurate at only one speed, right? Your BC can be accurate at the muzzle, or it can be accurate at 1,000 yards, but your BC is going to be changing gradually between those 2 points. And that introduces some error into a ballistic solution. Now, if you're using a custom drag model, okay, we've gotten away from the standard now. Throw away the benchmark. We're not conforming to a particular G1 or G7 curve, but every bullet has its own curve measured and modeled with Doppler radar, okay? And so when you're using one of those curves, you don't have any error due to the shape of the curve mismatching a standard. Now, this is most important when the bullet's slow to near the transonic range. So 1,340 feet per second is Mach 1.2 in standard conditions. So if your bullet slows below that, that's where most bullets have their drag deviate most from the standard. So in other words, most of the error that you would see in a BC-based solution is going to be transonic. F class out to 1,000 yards, you don't even get into that range. So you may not see any error at all in a G7 BC solution at 1,000 yards with F class. We make the custom drag models available for anybody shooting any range, but where they have the most benefit is if you're shooting into transonic, where the standard curves don't line up because they're different from your bullet.
How does the radar measure?
Yeah. So what the radar measures is velocity directly. Okay. It's sending a ping out. It hits the base of the bullet and it comes back. And based on the Doppler shift of the frequency in that signal, it knows how fast it's going. And it does that it pings the bullet several times. Well, you can set it for different things, but you can get it to ping several times per yard. So you can see your velocity change yard by yard.
How many times how many data points do you have? Let's say from 0 to 1,000.
Many, many hundreds. It's a point cloud. I don't even know how many points are in there.
Mm-hmm. But you said you could set it to different settings.
Yeah, effectively, it's a continuous measurement. Mm-hmm. I mean, unless you want to know what's happened between, we know your velocity at 601 yards and we know your velocity at 602 yards because we pinged it at those 2 points. And then that continuous curve just goes for as long as the radar can track.
The reason I'm asking, right, this is an arc, right? And yeah. I'm a machinist now. That just means I own machines. But in machining, right, there's no such thing as an arc. It's all straight lines, right? And what you do is you make the lines. The shorter you make those lines, meaning more data points, the more precise it's going to be on an arc, right? So if you want to do some roughing and quick machining, you make those data points farther apart, and the machine's going to move faster because it doesn't have to go from one to the other, right? It can, but yeah. It's not going to be as precise. And that's why I'm asking the question is how many data points, because obviously the more data points, the more accurate. Would you agree?
I mean, there comes a point where you just don't notice the difference anymore. And I'll be clear on something, the radar is not measuring the spatial position of the bullet. It's measuring its velocity as a function of time. So as soon as it sees it, it's like that bullet's going 2,800. 0.001 seconds later, that's about a yard of travel. It's going 2,799. 0.001 seconds later, it's going 2,797, and so on for 1,000 yards. And so you're getting a velocity measurement about every thousandth of a second, which is about a yard or half a yard at the end of the trajectory.
So you would get roughly about 2,000 points in right? Just if my math is correct.
Yeah, but the reason I don't really know how many points it is because we don't count them. We don't use the data that way. We look at it and say, so I'll let you in on how the actual software works, because I think that'll give a lot of insight into what the radar does and what it doesn't do, right? So we make a radar measurement of a bullet track, and we know the detailed velocity decay profile. That's what it measures. And then using software, we step through that and say, what would the drag have to be in order to go from this speed to this speed between these 2 points? Well, the drag coefficient would have to be this. Okay, that's what it is there. Now, what would the drag coefficient have to be to slow you down from here to here, the measured amount? Okay, that's what it is. And that's how we build the CD Mach curve, the CD custom drag model. And so now we have this model of how your bullet slows down. And I keep saying how your bullet slows down. That's not a trajectory, right? That's just a velocity decay history. But from that is what everything else is built. your wind deflection, your drop, your time of flight, everything gets constructed using that velocity decay radar track as the foundation. And so the way that we close the loop with this, say, here's the process. So a person comes up with a gun to the radar, fires a group of shots, and we say, okay, we got 10 shots on average. This was the velocity decay. We're going to construct this custom drag model from that test. Now that custom drag model, in fact, when an individual does it, we call it a personal drag model because it's for their gun and their bullets and their system. So they'll get a personal drag model uploaded into the library that's got like a code. And now whenever they go and use their AB software, they're going to build their gun profile using that PDM, right? They're using the very model that was created by the radar for their gun and their bullets. Now, when they go into a competition scenario, they're trying to calculate a trajectory. They say, all right, my target's here. Here's the atmospherics. Refer to the CD mock table that was generated from live fire to see what your drag is going to be so that you know what velocity decay profile you can expect, and then build the ballistics on top of that. And when that's done correctly, the results are, it's basically a closed loop. And so you're modeling the thing that you just measured, and it's all done within the same software that's meant to work together. So that's why it's very accurate.
So you're measuring speed decay.
Yep.
And then you use that to compare it. So what is, all the math and magic? I don't know how. The point is, what do you get out of that? Do you get a BC number, or do you get something different than that? Like, what would I put in my deal?
Yeah, fundamentally, you get a drag model, a CD mock curve. That's the fundamental result of doing a radar test. Now, if you want to then simplify that into a ballistic coefficient, you can. You have the data. You can say,
well, what I'm asking is, like, if I've never done one, obviously, right? And I just don't know what I get with it. Do I get if I shoot my rifle over or through your radar, would you give me, you said a custom drag model. Is that simply a number, or is that an actual thing that goes into your software that it's more than just a BC number? Because everything else out there is just simply BC.
Yeah. It's a table of numbers. It's a cumbersome table of numbers of, dozens of mock numbers and dozens of CD points that were measured. It's too cumbersome for manual input. So it's handled through the software behind the scenes. So if you did that and you went and selected, it's going to populate. It's not going to say what the BC is because it's not basing the solution on a BC. I mean, you could choose that. It's an option. When you pull up a CDM or a bullet from our library, you could select G1 BC or G7 BC or custom drag model. You can choose how you want to represent the drag for that gun profile that you're building. And of course, we advise to use the CDM because it's the most accurate. Where some shooters have a problem with their comfort level on that is they don't see a BC number being input, so they don't know what's being represented. And I get it. It's kind of unsettling to know you're running a ballistic solution and not know what the numbers are that are characterizing your drag. And that's why we left the BC options available instead of just doing the best one all the time. Because for those guys that want to know what their BC is or compare it to another solver, you can still run it with a BC input, but that's not the most accurate way to use the data.
I see. Makes sense. So, I'm going to look more into that. Like I said, I'm the reason I started thinking about this, and you're probably aware, as F-class shooters, we really don't have to worry about it too much. However, when you go to a world championship and they only give you 2-siders, it's like, man, if I could hit that X or that V ring when.
And they're convertible siders.
Exactly. So that's why, again, I learned this in PRS, but I'm like, whoa, I can use this in F-class if I could figure out. But I've tried it and not really very precise, right? And that's why
Yeah,
I
I
go,
mean,
well, if it's not precise for me, because it wasn't precise for me when I was trying to set up my PRS rifle, but now that I try to use it for F-class, it's still not precise. And I go, how can that not be when I have a known distance, and all these things, and still not right? What's going on here, right? And as you know, in F-class, we shoot. I mean, at least I'm going to speak for myself. I shoot a lot over a chronograph at 1,000 yards, and I gather a lot of data. And when I show up to a match somewhere, I range the target, and it's, because, plus or minus whatever yardage is going to make a difference. And it's still not perfect. So I'm it just got me to wonder what's going on here, which sent me into this search of trying to figure out what it is. And now I'm finding out custom drag models. But Caitlin was telling me that about this, I guess, radar derived drag curve. And again, this is all Greek to me, right? That's why I figured, hey, well, you're here, I'll ask you. But obviously there's a lot more research I need to do to formulate whatever's going to work for me.
Yeah. And to be honest, I don't know that your struggles with finding perfectly accurate fire solutions are due to your lack of understanding in CDMs or radar derived. Like that's way deep in the weeds stuff. I think there's probably a list of other things that would more likely explain why you're seeing error between your predicted and actual drop. Things like, scope tracking, if you dial 25.0 minutes and your scope gives you 25.5 minutes of actual adjustment, there's only one way to know that, through a direct testing and measuring of it.
I do target tests and everything.
Yeah, that's good.
Anyway, again, this is just, but mainly this was itching from back when I was doing a lot more PRS, and it just seemed like I was never dead on. But anyway,
here's another tip for fire solutions in F-class. So suppose you go to the line with your ballistic device, take all your measurements, and you estimate 25 minutes of angle for 1,000 yards. You dial it on, and you're a half low. Don't know why, but you're a half low. Well, so later in the day, you go to another yard line, and it says you need 27 minutes. Now, you're probably better off running 26 and a half than 27. See what I mean? Because if you have a delta between what's actual and predicted, that delta is going to be a more reliable piece of information than a raw calculation. You know what I mean? So like if you have a half minute more drop than predicted, and you predict a different amount for different yard line, chances are you're going to be a half minute low from there too.
Okay.
More or less, you won't know why necessarily, but it's a good bet that if you're a half minute low at 1 yard line, you're going to be a half minute low at another yard line,
every yard
plus
line.
or minus low.
Yeah, because we don't move, but we only move 200 yards, right? Like all day.
Yeah.
So that's not that difficult. You discussed the sampling, large sampling at the beginning, and you talked about that, how that could influence how we develop loads. And as you know, in F-class, it's all about load development. We believe that a lot of matches are won in the reloading room. What is your load development now that you would suggest that somebody try?
Well, it depends on what you're trying to do, what you're trying to accomplish. If you're talking F-class application, in particular FTR.
Well, let's do F-Open.
The thing about F-Open, yeah. So in F-Open, it's a bit more open-ended because you've got so many different cartridges. Like the reason I went FTR is pretty much everyone's shooting 308s, 200 grain class bullets, and a short list of powders. So the load development for a 308, I hate to say it, but it's hard to do better than just taking a sampling of what a lot of guys are doing that's working. There's no reason that wouldn't work for you. And you can get a large sampling from that because many people are doing something very similar. In F-Open, that is where you need to do more of your own load development, because not everyone you're shooting against is shooting the same cartridge with the same bullets. So, load development, again, with what we know about the natural statistical variations and sample size, I used to be way more reactive to tests and load development than I am now. And it's because of what we've seen with these large scale tests. So there's goals that you have that you can accomplish through hand loading directly. And I think the biggest thing that you're directly taking control of with hand loading is your muzzle velocity standard deviation. I think that is the number one thing that you are optimizing with hand loads. A lot of guys will say that precision is what they're optimizing with hand loads. And I don't see it that way. I think that in terms of component selection, by the time you selected, you've got your gun built, okay? I think most of your precision is established with the gun and the class of bullet that you're shooting. And then, look at the quality of the brass, quality of the bullets. If you're using top quality components and you're putting them together well, I think that is the majority of what drives your precision in an F-open type scenario. Of course, you can do tests all day long and say at this seating depth, the group was this, at this seating depth, the group was that. But you can do that exact same thing if you're shooting the same ammo. The same ammo will shoot two different size groups, just like when you move the seating depth 5 thou. So my load development in recent years has really dwindled down to, I'm going to find a load that I know is never going to go over pressure in any condition of fouling or temperature. That's number one. That's a reliability and safety thing. And number two, it's a load that has at least good enough precision to do what I'm trying to do. Like if I had an F-open gun and my precision was 1 minute of angle, well, that's not competitive, right? At 100 yards, my groups are 1 inch at 100 yards. It's not competitive. But if I get the gun shooting, half or 0.6, 0.4, something around there.
You're still not competitive, Bryan. Anyway, I'll let you finish. I know where this is going, but
I'll comment on that. My FTR gun averages 0.6.
Yeah.
And I shot that gun against a lot of competitors who had, or at least claimed that their FTR guns averaged 0.3, 0.4, 0.5. And I beat a lot of those guys with my shitty 0.6 average group size. Now, whether some of that is in how we characterize the groups, like, some shooters will throw away bad groups, throw away flyers. First of all, I don't do that. And so maybe the way I characterize my gun is 0.6 and they characterize theirs as 0.4. That might be a difference in how we characterize them rather than that there being a genuine difference in them.
How long ago did you quit shooting F-class? About 10 years by now, roughly? 8?
The last time I shot F-class was the World Championship in 2017. And I was third in the world in that tournament in Canada. That's the last time that I shot F-class competitive. Okay.
Yeah, it's and the thing about group size versus in F-class, because it's a score. We shoot for score, right? You need precision and accuracy. That's where you can make up a lot of ground if you're a better wind reader, if whatever. So I think that's where things get muddy in a sense of it's not straight accuracy that's going to define whether you win or not, right? It's going to be
not straight precision. There's a lot of decision making and judgment involved.
Right. Like if you have a really good gun and it's dead calm, you're going to do really well. But if you have a really good gun, let's say a 0.4 gun or 0.3 gun, and somebody else has a 0.6 gun, they both going to hit the 10 ring, correct? However, the 0.6 gun has less room for error because the group is bigger, right? But if the person that's shooting the 0.3 gun can't read the wind within half MOA or 1 MOA, then they don't stand a chance against the person with a bigger gun that can read the wind within a quarter MOA or half MOA. That's what I'm getting at. So I think it's hard to say, well, my gun was worse, but I beat better guys. I think in Ventress, where they shoot for a group, that's probably more where we could use that example. But that's a whole another world and that I've never played in.
And to add to your point about the precision is only one aspect of it. Like wind reading is obvious. In my opinion, wind reading is the biggest decisive factor in F-class shooting, hands down. Yeah, you get days where the wind isn't blowing, but you don't get a whole tournament where the wind isn't blowing. Someday, morning or afternoon, the wind is going to blow, and that, in my opinion, is what is going to stratify the standings the most, is what you do when the wind blows. And with my point, my shitty 0.6 precision F-class gun, that's only one aspect of the performance, right? Like what I said a minute ago about the biggest thing you're doing with hand loads is minimizing your muzzle velocity spread. If I'm shooting 0.6 minutes at 100 yards, but my SD is 4, and I'm shooting against somebody with a 0.3 100-yard group average, but their SD is 7, I think I'm going to beat them at 1,000 yards.
Yeah, that makes sense.
And so that's
I can
why
get on
I
board
work
with
so
that.
hard.
I can get on board with that. Now, so this is how I've simplified my reloading, and I tell people, look, I just put things in 3 different buckets. Number 1 is combustion. That's your ES, SD, whatever influences combustion, that goes into that bucket. And that's going to be your brass selection. That's going to be your primer, your powder, your case capacity, right? I mean, for obviously for FTR is simply just 308. But obviously your powder type, and obviously how much powder you put in there, and bullets going to influence that, neck tension, everything that can influence combustion goes in that bucket. So you got to handle all of that. And then you have what I call barrel harmonics, right? Like you ignite the powder, but if your harmonics are off, and I say, tuner or seating depth, does seating depth matter in your opinion?
I'll reframe your question. Under what conditions does seating depth matter, and do those conditions apply? So first, I think that the sensitivity to seating depth depends on the type of bullet you're shooting. So hybrid bullets, I tried my best to design bullets based on what I thought made them jump sensitive, to be the least sensitive. And for the most part, I think I've accomplished that, because many guys who have done seating depth tests on hybrids and tangent nose bullets as well don't find a strong correlation between group size and seating depth as compared to VLD style bullets that are known to be way more sensitive to seating depth. So in the question, does seating depth matter? I would say if you're shooting a bullet that is sensitive to seating depth, then it does. But not all bullets are equally sensitive to seating depth.
I think they're all sensitive, just not to the same degree. That's my belief.
Yeah, I think we're saying the same.
Yeah. So again, I said, okay, once you handle combustion, that means you have low ES and SD, right? That means you have a happy load, happy combustion, right? And then from there, because you hear this all the time, said I have a load that shoots extremely low SDs, but the groups are really big. Well, if you have good components, that should not happen. So something else is not happy. Well, if you change your load, more likely you're gonna throw that unhappy. Now it's gonna be unhappy. So that's where I go. Okay, once you have a low SD load, ES, SD, transition over to harmonics. Play around with seating depth, because it may simply be that you're out of tune and you're seating depth, and that might just bring it in and align it to where now you have low SD, small groups, you're happy, right? And of course, tuner. That's for me, I've transitioned to strictly tuner. I just know where I just seat the bullet at the same place, and then I just do the rest with tuner, and then the rest I put in a bucket called external ballistics, which means if you have a gun that's shooting 0.4 or 0.3 at 100 yards with extremely low SDs, but it doesn't shoot good at 1,000, I believe the rifle did all it could. And now you need to look at your bullets, because there's a reason they're not all staying together.
Mm-hmm.
Right. So that's how I simplify things. And that's helped people to not, because they try to attack everything at once, right? And they end up really confusing themselves.
It helps a lot to simplify things, at least so that you have a systemized way of thinking through it. So what I'll say to your three buckets, the combustion side, the internal ballistics, I agree, and I'll only emphasize that in my opinion, the most important things in that combustion or internal ballistics is to match your primer to the powder charge and volume. I've seen dramatic changes in ESs and SDs with just primers and nothing else. So what's that tell you? If you happen to have the wrong primer for the powder you're trying to use, you're never going to do well with that. And so one of the first things I do is, once I narrow in on a powder I want to try, I'll just pick one nominal load and start running groups of different primers. And if, this primer could only make the best SD of 18, but this primer made an SD of 4, well, that's the ball game right there. That's the majority of it. And so matching the primer to the powder, I think, is the most important part. And then the powder, and this isn't so much of a thing in F class because all the barrels are long, but when you start doing load development for like 24, 22, 18-inch barrels, then you have to consider how fast burning your powder is, and that it's all getting burned in the barrel. Because you can have everything is consistent in the world, but if all the powder isn't burned when the bullet comes out, that remainder is variable each time and is going to give you big problems with ESs and likely groups as well.
Can I share my findings with you on primer testing?
Please.
That's how I used to test primers, how you just described. And I found myself chasing my tail, because let's say we have one powder and one primer, right? And as you vary the powder charge, it's going to give you a load that's going to have low SD and one that's going to have large SD, right? If you cover a whole, 2, 3 grains, 4 grains, whatever the test covers, right? You're not going to select the powder and a primer and throw any load, any charge at it, and it's going to be low SD, correct?
This may be the crux of our difference in opinion, because I believe when you find the right combination of powder and primer for the cartridge, it is not sensitive to powder charge within many grains. Like, you could be at a low of, an 80% fill or a high of a 95% fill, many grains apart. And if that's the right primer to ignite that powder in that volume of a case, you're going to see the same SDs all the way across. Now, small sample testing may mislead you into thinking that one particular charge is way better than another. But we did this test also with ladder tests, where we repeated it. And those things that look like flat spots, when you do the test enough times and average it, they're not repeatable. So when the match is genuinely good, you almost can't mess it up, is what I've found.
Okay. Well, we do, as you know, we shoot 20-shot strings in F-class plus sider. So it's not small samples, 25, right? And I've seen it to where, simple charge can make a difference. But again, this is just me. This is my findings. So what I found, that at least for me, the way I test primers is I don't pick one powder charge. I pick a range and I test one primer, and then I pick a range and pick another primer, and at least cover a range so that to see if there's a happier place. And what I find is typically it's not the same load that makes the primer or the whole internal ballistics bucket happy. but that's just what I have found. But it may be that's another thing that I'm looking into. I'm the large sampling, but again, we do 20, 25 shot groups in F class, right? And I keep chronograph data and all that stuff. But again, that's just how I've settled on testing primers, is cover a range and see, but anyway, that's why this is called the discussion.
Yeah. And I'm sure like there probably are, and well, I know there are cases where like the right combination with this level of powder is the right combination. But if you change that amount of powder too much, then maybe a different primer would be better. And so, yeah, it's a discussion. And like you said, we can only share what testing and findings we've had. And that's how I've come to view it, is the most important thing in that combustion bucket is the combination of primer and powder. And if you have that right, then a lot of the other sensitivities kind of melt away, is what I've seen.
What about, I can have just a tremendous load that shoots just single digit ES for 25 shots. And then I put that in another barrel and all of a sudden it doesn't. Like you would think that combination primer powder would work universally, but it doesn't. What do you think's happening there? Or at least in my belief, it doesn't.
Yeah. So one way that happens, that I used to, probably many people have gone through this cycle, is you get a load optimized for a competition barrel and you run it hundreds, maybe thousands of rounds, and it's your go-to load and you love it. And barrel comes to the end of its life, you need to replace it with a new barrel, and you do your best to everything the same reamer, barrel length, same twist rate, barrel maker, everything. Well, now you put that load in there, and like you said, it doesn't perform the same. Well, this is something that I forgot to mention on barrel break-in and life cycle. But when we talked about velocity migration and picking up speed those first few hundred rounds, another correlate to that process is the standard deviations change as well. So we have this batch of ammo, and when the barrel is new, average velocity is the lowest and standard deviations are the worst, okay, when the barrel is new. As that firecracking develops and as that back pressure builds in a fouled, rough barrel as it's breaking in, not only is that increasing the average velocity, but through the same mechanism of how it's affecting the powder burn, it's also forcing a more consistent burn, and the SDs go down. So the same exact ammo, the same exact load that was giving us 15 feet per second SDs out of the new barrel when the load is slow, just keep shooting it and it speeds up and the SDs go down to 4, 5, 6 feet per second. And so, but what will happen, like with the average, what I used to do is I get that new barrel, try my old load, and it was too slow and the SDs were too high. And I, not knowing that was just a property of barrels, I guess I got to develop a load for this barrel. So you start going round and round and round. And what do you find by 200, 300, 400 rounds? Lo and behold, you often will converge back on the same load that worked in your last barrel. And you're like, oh, that's weird. But you're up and running again. So a lot of those load development practices that take place early in a barrel life, I think are happening because the break-in effects and the life cycle effects of the barrel are not understood in those first. I don't take any load development feedback from a barrel seriously until after 200 rounds, because it's still changing. It's still settling into what it's going to be. And when you take a load at the end of a barrel life and try to run it in a new barrel, of course, I say now, of course, that's not going to work because the barrel is different. Now, if you're talking about two barrels that have the same round count on them and you run the same ammo in those and get different, then I guess I don't have an explanation for that. But if it is an old barrel versus a new barrel that you're sharing loads with, absolutely, I wouldn't expect them to perform the same.
Yeah. Well, it's just interesting because, we have loads that are close, but not the same. Like it's and sometimes we get barrels that shoot the same load, right? But it's not a guaranteed thing, right? And again, we're shooting F open. You talked about a .3 gun at 100 or .6. Like my baseline is .3 at 1,000 or 3-inch groups. If I'm not consistently shooting 5-shot 3-inch groups, that rifle or that barrel does not go to competition, right? And it's again, I don't know. I'm still learning and hoping I can figure out how to shoot 1-inch groups at 1,000, and then that's going to give me 9 inches to be off on that target versus
the target
2 or
just
3
gets bigger.
Oh, it gets drastically bigger if your groups are smaller, but just more real estate. But it's an ever. I'm always learning, always asking questions, and keeping an open mind. And man, if I just like my podcast, believe the target. I can read, I can test, I can ask, but ultimately I shoot at the target, and if whatever the target tells me, it's really the end game. Which, would you agree that that's probably what we all should do?
Absolutely, with a caveat that in I forget what century it is now that Impressionist painting was popularized, but those artists that first started doing that, they were aware of what they called the beholder's share in their art. Okay. And the beholder's share in the context of Impressionist artwork has to do with what your mind will imply is there. Like you're psychologically filling in the blanks of a picture. And I think that when shooters are looking at a target with a bunch of groups on it after a test of some kind, yes, you have a target and you should believe it, but you should also be aware of what your share is in interpreting those results. All for sure is these holes are in these positions on this paper. Everything beyond that is an interpretation. And early on, years ago, when I was in that position of looking at a target with a bunch of test groups, I was looking, you do it to find causality. So when the test is over, you're assigning causality. What made this group big? What made this group small? I look at targets very different now. I look at a target that's got groups from 0.4 to 0.7, and they all look the same to me. That's because of the arc that I have taken through my, shooting competition and through my career, and the large sample size testing that I've been exposed to is a 0.4 and a 0.7 group don't look different to me, really. Now, if I shoot 10 groups and they average 0.7 in a row, and then I change something and 10 groups now average 0.3, that's a difference. But one group doesn't tell me anything. I mean, if I shoot one group and it's 6 inches at 100 yards, that tells me something's broken. But if my average is 0.6 and I fire a 0.8 group before going to a big match, I'm not running around with my hair on fire trying to figure out when my gun's broken. I understand that a 0.8 is a sample from the population that my gun always shoots. So I do agree you have to believe the target, but I think the strong caveat there is you're interpreting a lot of what you see. You interpret a lot of the meaning into what you see. And that's where the subjectiveness comes in. And that's where shooters will disagree about what matters and how and why it matters, because we're looking at these targets trying to assign cause and effect. And usually the sample sizes are too small to do that legitimately.
Makes sense. Now, expanding knowledge. I wrote this down because that's actually why I started the podcast. I lived in a bubble of F class, and I realized, wait a minute, like if I'm only talking to the same group of people my entire life, I'm just gonna know what they know. They're gonna know what I know, and that's it, right? So I said, I'm gonna start having conversation with bench shooters, and that's where it started with Speedy, because he's a friend of mine. And when him and I talk, it gets wild, and I just sit there and listen to him because it's very entertaining and very interesting, everything he has to say, being a Hall of Fame bench shooter. But so expanding knowledge, but I as much as I respect Speedy and as much as I respect a lot of shooters, when they tell me something, I don't just say, well, Speedy said it's going to work, so I'm just going to go do it. Mm-hmm. I test it. And a lot of people use you as an example. Well, Bryan said this, so that's it. That's the end game. That's how it is. Is that how you think they should take it, or they should take it? How should they take your writings, your findings?
Yeah, the implied caveat in every single test result that we do and publish, I try to state it as often as possible. It gets cumbersome to attach to everything, but the implied caveat to everything is, under the conditions that we tested, these are the results, right? This is what happened under the conditions that we tested. It does not apply to anything outside of that. It is a contained result. So if we test annealers are a great example. It's something that's misunderstood, and I'm glad I've got this opportunity to talk to a crowd who cares about annealers. Our work with annealing was misrepresented in the community by that same mechanism that you said. Well, Bryan said this, so therefore it's, well, what the reality is, annealers are meant to anneal brass. And the annealer that we tested, 100% annealed brass. I'm sure that all the metallurgy was accurate, well documented, and it annealed that brass. However, that's the question that I was exploring is, does annealed brass affect standard deviations in muzzle velocity or not? In the particular test cases that we did 223 and 308. And I won't go the whole details, but the conclusion was we could not detect a reduction in standard deviation in brass that was annealed versus brass that wasn't after many firings, and the community kind of took that the wrong way. They took it as a blanket statement, like annealing doesn't work. Stop you right there. Annealing does work to anneal. The question we asked was, does that annealing affect this particular variable? And in the two cases that we tested, it didn't. Full stop. That is the end of it. Now, annealing has other advantages, right? Like your brass will last longer without cracking. It probably resize more consistently if you anneal it. There are benefits to annealing, but I'm trying to detect a benefit in the end result of shooting. And you can only test one case at a time, And I'm sure there are cases like you get the right combination of cartridge, primer, powder, bullet, gun. I'm sure there are cases where annealing will reduce your SD. But in the examples, like if you're shooting a 308 with these powders and these bullets, annealing probably isn't going to reduce your SD based on our test. That's all. That's the end of the result. It's really a very limited result. And what we hope for is for others or ourselves down the road to repeat the test and expand and look for applications where it would matter, right? Back to that, what conditions need to be present for this to make a difference, and are they present in my system? What I'd love to know is what are the conditions that make your standard deviation sensitive to annealing? Imagine if we knew that, then you wouldn't have to make blanket statements. You could say, look, if you're shooting, I don't know what it is, but this combination of variables, we've found that annealing brass can cut your SDs by 40%. I'd love to find that case that shows where it works. But when we looked, the only two cases we looked in, it didn't impact standard deviation. So back to your question, the implied caveat to everything that we say is why nobody should take blanket statements unquestioningly, is that the caveat that's on our testing is, this is what we were looking for, and this is what happened. Don't draw any conclusions outside of that, because then you're painting with too broad of a stroke.
Yeah, I've been sharing my findings and whatever I can find and try to help the community and try to grow the sport on my channel for a decade now. And oftentimes people confront me and say, well, back in 2012, you said this, and now you're saying that. So you obviously don't know what you're talking about. And I said, au contraire, my friend, I'm keep learning and I keep testing. And at the time, I 100% believed that's what worked. But through testing and keeping an open mind, I have found since that, guess what? I was wrong. And this is what I believe to be the best now. I may be wrong right now as I'm telling you. However, as I am telling you this, I believe I am correct. So that's something that often happens. Not often, but it has happened to me. And, I believe, how you talked about large data sampling. I think that's actually what we're dealing with. The sample of my data is pretty small compared to the entire samples of data that are out there, because you said you tested annealing. Well, that was 2 rifles out of how many are out there that are annealing, right? So
right.
It's just interesting.
That's 100%. What you just described is the scientific method, right? You have a best fitting hypothesis for the available observations, and that will remain the best explanation for something until more information is available. And then if enough conflicting information is available and convincing enough, well, then you have to change your beliefs to align with the newest best data. And that's how science moves us into being less wrong continuously. I don't know that we'll ever be 100% right, like you said, but the goal is to be less wrong by following the best evidence that's available at the time. And this happened to me too. Like when you asked me years ago, the best way to sort bullets, whatever I had in my head when I answered with base to ogive was based on some experience, but that was limited experience compared to what I have now. And so now I try to imply a lot of the conditions from who's asking me, right? If I'm on a F-class range and someone asks me, how do I sort bullets? Well, I'm going to assume they're shooting copper jacketed lead core bullets, probably without plastic tips. So I can infer a lot of those conditions and say, well, probably based, and plus I've learned since then too. So yeah, I think it's a mistake to discredit someone because they've changed their mind about something. I mean, that's evidence that they're open-minded and willing to consider new evidence. So, but it's just, we'll have to take those licks as we go, because some people are always going to use opportunities to discredit, whether they really see it that way or whether they're compelled to see it that way for other reasons. I'll keep following that trail.
Yeah, well, I've been wrong a lot. That's all I could say, and I'm not afraid to admit it. And because I know that sometimes I'm wrong, actually the majority of the time I'm wrong. That's why I always keep searching and learning and asking and testing, because if I go under the assumption that I'm wrong, I get to learn a lot more. Mm-hmm. Have you ever been wrong?
All the time. If you ask my wife, she can give you a list chronologically or alphabetically, however you want it. But yeah, I've been wrong with shooting things in my career also. It's part of learning. None of us you don't live life from the end back. You live it from the beginning forward, and you accumulate experience, and you should change your mind. You have to be wrong. And, assuming that you're wrong is the very thing that opens your mind to looking for other things that are more right. If you think you understand something, then you're closed off to potentially more accurate beliefs. So there's just an unwritten, unspoken tone in a scientific community that anything that's stated could be wrong. In fact, probably is wrong to some extent. And the effort that we're making is to be continuously less wrong.
I agree with that. So, what makes a bullet accurate? What makes, like your 180 hybrid? That's got to be, I don't know. Is that, I'm gonna say that's your best work ever from an F open shooter standpoint. What makes a bullet good?
So if you're talking about what makes a bullet inherently precise in many different rifles. So one fundamental thing that's at the foundation of precision bullet design and building is the balance of the bullet. And I'm talking about the static balance around its rotation. So this is where if you hear, J4 jackets have 0.3 of an inch run out or less, that's important because you want that lead core to be centered in the jacket. So when it's spinning at 200,000 plus RPMs, and comes out the barrel, it's not flying off in all different tangent directions. So that's not even in the design of the bullet. That's in the manufacture of it, right? So you need well-balanced bullets so that when they're spun at an excessively high RPMs, it's not causing dispersion. And that's something that every manufacturing operation gets better at over the years with better equipment and technology. And what it's allowed us to do is make better, longer bullets than we used to be able to. And so, you go back 50 years and try shooting good groups out of an 8 twist anything. The bullets, the imbalance that was inherent in bullets 50 years ago prevented them from even approaching the kind of precision we get today in a fast twist barrel. But whenever you improve the consistency of the bullet, it's less susceptible to dispersion from spinning it fast. And so that lets us make longer and longer bullets, faster and faster twists without suffering precision. All right. So that's across the board, state of the art stuff. But as for bullet design, couple things about the 180. It was one of the first hybrid bullets. And it was made with we were on the fence about 2 different knockout pin sizes for that. We could have gone a little on the small side, which makes for more problematic ejection from a bullet forming die, but makes a smaller MEPLA and a higher BC. Or we could go with a larger, more robust diameter MEPLA for knockout pin and have a bullet that's easier to make, more consistent, but it has the downside of having a slightly larger MEPLA. And we went with a slightly larger MEPLA. And I think that was the historical success of that bullet at this point has been a good lesson in that trade-off. In the trade-off between high BC versus consistency, it's very tempting to go for high BC each time because that's going to help you in the wind. It's going to help you sell bullets. High BC is just attractive. But when you look at what you have to give up for it, you're giving up winning matches for it. You're giving up shooting the smallest groups you could be. You're giving up the most consistent BCs that you could have. You're giving up all the stuff that wins whenever you try to push too far towards optimizing one thing, right? So that bullet has a little bit larger MEPLA diameter than would be typical. And I think that has helped it be a more consistent bullet in the end. Again, the hybrid ogive helps it be less sensitive to jump as well. It'd be really good to ask the production guys at Berger what makes that a good bullet, because they might have insights about how the jackets are made, how the cores are made. Like that bullet might fall into a special zone from a production standpoint, rather than just an external ballistic and flight performance.
Who would I talk to over there?
Some things are just easier to make better than other things.
Who would I talk to over there?
David Hamilton.
All right. I always ask people to recommend somebody I should talk to, and I think you just did.
Yep.
Seems like there was something else I wanted to talk about.
We covered a lot of stuff, I think. What else could there be?
I don't think there's. All right, let's. My goodness. So obviously tuners, right? Your tuner testing.
Mm-hmm.
We've been at this almost 2 hours.
2 hours. Yeah. That seems like it probably should be another conversation.
All right. It's going to be a lot of heartbroken people over this, but we're pushing on 2 hours, and I want to cover this topic in depth. All right. So you're going to come back, or what are we going to do?
Well, you could come on my podcast. We could talk about it there. The Science of Accuracy podcast.
Okay, we can do that. Let's do that. Let's schedule that. And I know a lot of people probably tuned in to hear us talk about tuners, but I think what we covered was very good information that where whichever side of the tuner camp you're on, you're going to take some really good you're going to have a really good takeaway from this discussion that we've had. So let's do that. Let me come on your podcast. We'll talk about tuners, and just let me know.
Yeah, that way we'll have the time. We can just dedicate the whole thing to it, beginning to end, and not try to cram it in to the end of a 2 to 3 hour podcast.
Yeah, let's do that. Bryan, it's been amazing. As always, it's good talking to you. I used to talk to you a lot more when you were an F-class shooter, but it's
I've enjoyed seeing you do well in F-class and seeing your channel grow. Lots of people that approach us with questions and stuff mention that you've helped them with other things too. So you're definitely you're helping a lot of people with your channel and with what you're doing. So it's good to see you. I haven't seen you in a long time, but I'm glad to see you've been doing good things.
Thanks, Bryan. All right, well, let's do that. And until then, keep them centered.
All right, man. Thanks for the talk.
See ya. Bye-bye.
See ya.